Hi students, today we are going to study how the chi-square test is used for testing the goodness of fit, association and homogeneity for a given data. So this test is for the categorical data. That means we have to have an attributes, qualitative characteristics to be tested. So before going in detail, first we summarize what is goodness of fit test, association and homogeneity. So goodness of fit test is a chi-square test used to find out whether the fitted distribution, that is we have a set of data, we know how to fit the distribution like binomial, Poisson, normal, etc., which you have already studied in distribution theory and estimation. So we have fitted a distribution for a given data, and we wanted to know whether the fit is correct or whether the data actually follows the fitted distribution. For example, if you fit binomial distribution and we wanted to confirm that the data which we fit the binomial distribution is actually came from a binomial population. So that is what we are doing in goodness of fit test. Then test of homogeneity is a test for assessing if two or more populations are homogeneous. That is, they are alike with respect to the distribution of some discrete variables. Now finally the test of independence. This test is equivalent to that of correlation. So we have a two quantitative characteristic and we want to find any relation exists between these two variables, then we do correlation. So we find the correlations, and if yes, they have a correlation, then we say that the two variables are related. Likewise, if we have two attributes, that is the qualitative characteristics, two or more, maybe two or more attributes, and we wanted to check whether these two attributes are or two qualitative characters are related, then we go for the test of independence or test of association, also called the test of association. So these are the three tests that we have to study in the syllabus. So that's your last syllabus, and this is called a non-parametric test, where because here we cannot assume any distribution for the given data. So we are going the first how to test the goodness of fit test. Again, I tell that what is a goodness of fit test. The test involves a comparison of observed frequencies of the occurrence of classes with the predicted or expected or theoretical frequency. So what we are first doing is we first fit the distribution to the data, then we find the expected frequency, which we already done in the earlier classes. So and with the difference or with these two set of expected and observed frequencies, we calculated the chi-square statistics and check whether it is significant or not. So that is what just in summary we do in chi-square test for goodness of fit. So here we assume that the given data follows some specific distribution. So null hypothesis is that the given data follows a specific dot. That is, it not the data is binomial, Poisson, normal, etc. Any data, any particular type of distribution. And alternative hypothesis is that the given data does not possess the distribution considered in null hypothesis. Okay. Now, what is chi-square test of fit? So, here we calculated a chi-square statistics, which is defined as sigma equal to 1 to k oi minus ei squared by ei, where oi, o1, o2, etc., ok are the frequencies that we are given in the data. So we have given a class or values, x values or classes depending on the distribution which we wanted to fit, and then the frequencies. So that frequencies are called OI, O1, O2, etc. Okay. So the given frequencies are called observed frequency. Then what we are doing is we calculate the parameters or estimate the parameter value based on the moment estimates, Then we find out the distribution, or we fit the functional form of the distribution, and putting each of the x values given, we can able to find the corresponding probability of the class or the values. Then with if we multiply this with the total number of observation and approximate it to the discrete case, it is approximated to whole numbers. So you get the expected frequencies, which is En. And after these calculations, we are going to calculate chi-squared, which is given as chi-squared equal to sigma equal to 1 to k oi minus ei squared by En. So this has k minus r minus 1 degrees of freedom, where k is the number of data that is given. So k is the number of data given, r is the number of parameters estimated, and minus 1. So the chi-squared that here given here, give this chi-squared follows uh, chi-square normal chi-square distribution with k minus r minus 1 degrees of freedom. So you can obtain the critical values from the chi-square table with the k minus r minus 1 degrees of freedom for a given alpha, and you can make the decisions. So before going to the decision part, how to accept or reject the hypothesis, first we summarize how to do the goodness of fit test when you are given a real data. That's all. The firstly we can have a tabulated data, either grouped or ungrouped data with the values or the classes and frequencies. So from that we have to calculate the estimators of the parameters of the distribution. After that we can obtain the expected frequency into NPI, where Pi is the probability of distribution. Probability of the observation falls in a particular class, that is calculated from the theoretical distribution. Then calculate chi-square using this formula. Then we can take the calculated or critical values from chi-squared alpha for a given alpha from the chi-square tables with k minus r minus 1 degrees of freedom. So if the critical value is chi-squared alpha is less than chi-squared, sorry, if the calculated chi-squared is less than chi-squared alpha, our fit is correct or fit is very good. Otherwise, if chi-squared is greater than chi-squared or chi-squared alpha, or that is the critical value, we reject the hypothesis and conclude that our fit is not good. So because before going to construct the test or going to do the test in practical situations, so you have to make sure that the number of samples, so the total number of frequency should be more than 50, and the theoretical frequency that when you calculated it should at least 5. So if it is less than 5, you have to add the corresponding classes to make it greater than 5. So the degrees of freedom should be carefully determined by the criteria. So if the hypothesis directly fits the theoretical or expected frequency, and you are not going to find out any parameters, estimate any parameter values or estimate any parameters, then the degrees of freedom is k minus 1. If you are going to estimate r parameters, then your degrees of freedom is k minus r minus 1. So k is the number of classes of the final group or number of observation of the final data based on which you calculate the theoretical frequencies or and the chi-square. So if on some theoretical frequency, if you have 5 classes and for one last 2 classes the theoretical frequency is 6 and 1, then we are going to add that one and so the k is reduced by 1. So should be careful when you take calculate the degrees of freedom. Okay. Now we go for a next sample. So we are given a data and we fitted the binomial distribution for this. This is already you are done in the estimation classes. Okay. Again, here we have n equal to 4. So because x varies from 0 to 4, so that is n equal to 4. In binomial, x varies from 0 to n. So here n equal to 4. And the theoretical frequencies are given, and observed frequencies are given, and we can fit the distribution by only the p is to be estimated. So the p is by moment estimate, it is x bar by n, so which is calculated at 0.46, and q cap is 1 minus p cap 0.5. So the theoretical distribution that we fitted for the data is fx equal to 4x 0.46 raised to x 0.554 raised to 4 minus x. X varies from 0 to 4. Now, now we now we calculate the observed frequencies. So, which is nfx. So, corresponding to x equal to 0, 1, 2, 3, 4 x, we calculate nfx, and then we approximate it to the digital all numbers, as the frequency cannot be uh, decimals. So, they are all numbers, so they calculate it, and as you see, we calculate oi minus ei squared divided by EA, and we sum it to be 1.094. So now we calculate the tabled value. So here we have k equal to 5 classes. The number of parameter estimated, k equal to 4, actually k equal to 4 classes, is 4 classes 0 to 4, and the number of parameter estimated is 1. So the degrees of freedom is k equal to r minus 1. So it is 5 minus 1 minus 1, 3. And from the chi-square table, which you know how to observe, for a given alpha equal to 0.5, if it is particularly not given any alpha, default alpha is 0.05, is 7.81. So here what we call, you get the calculated value is 1.094, and the critical value is 7.81. Since the calculated value is less than the critical value, we accept H naught, and conclude that the given data follows binomial distribution. Okay. Now next we consider a Poisson distribution. So here we have to estimate one parameter again called lambda, which is x bar. So you calculate the sigma x f by n, which is given to you lambda as 2.90. So the theoretical distribution is fx equal to e power minus 2.9, 2.9 power x divided by x squared. So the hypothesis which we are going to test is H naught, the given data, that is this data 200 data give follows Poisson distribution, and then does not follows Poisson distribution. So the first next step is to calculate the observed frequency. So that is given in this table. So observed frequencies is 14, 31, 47, 41, 29, 29, 10, 7 and above 7. And the expected frequency, that is NFX, approximated to the odd number is given will be obtained as 11, 32, 46, 45, 32, 99 and 6. So we can able to calculate the chi-square, which turns to be 1.996. Again, sorry. Again, from the tabled value, we can able to find out the chi-square value as 12.59. So the critical value for chi-squared alpha for alpha 0.05, 5% level is 12.59, Here also the critical value is more than the calculated value, so we accept H naught and conclude that the given data follows the Poisson distribution. So now finally we can look a problem which specifies the distribution. So this distribution specifically specifies what is the binomial distribution. So here the degrees of freedom should be k minus 1. Okay. So we are not going to estimate any parameters. So the question is, we are given 5 dice and asked to throw it 96 times, and the test the dice, and we wanted to test whether the dice are unbiased or not. If the dice are unbiased, then it follows binomial distribution with p equal to 1 by 2, and since we have the value 0 to 5, 1, 2, 3, 4, 5, so the frequencies is 17, 19 and hertz. So it's a given. So since this one is given that dice are unbiased means both the even number turn up or odd number turn up will be in the same way. So that is what we are given. So we have the binomial distribution with p equal to 1 by 2 and n equal to 5. So the theoretical frequency should be calculated directly from this formula. So you need not wanted to find out the estimate of p. That is, you don't want it to go for x bar and x bar and then give x bar p equal to x bar by 5. That not required here because it is given to be 1 by 2, because then only the die should be unbiased. Okay. So this example we have calculate again the theoretical frequency and observed frequency. What happened is, you can look into that this the observations corresponding to 5, the theoretical frequency is 3, so which is less than uh, 5, and again the theoretical frequency corresponding 0 is also 3. So you have two values, one here and one here, which is less than 5. So what we are doing is we are adding this with this table, this observation, and the 0 and with 1. So the new table that we are observing is 5 over 4 with observed frequency T 26. Here the theoretical frequency is 3 and the next class it is 15. So if you add these two, you get 18 as the new frequency. So your x is 5 over 4 and the theoretical frequency is 26, and sorry 18, correspondingly you have the earlier two theoretical frequencies, observed frequencies, so that to be 10, 26. So what you have, the frequencies 26, 35, 24 and 11, and corresponding specified frequency as 18, 30, 30 and 8. So here you have only 4 classes, so your degrees of freedom is 4 minus 1. Since there is no estimation is done, k r equal to 0, so the degrees of freedom is 3, and we get the chi-squared is 8.31, and from the degrees of freedom it is 7.81. So what we happened is 8.31 is greater than 7.31, so we reject the hypothesis. So it's what we conclude that we need reject the hypothesis. The null hypothesis is that the given dice are unbiased, and the alternative hypothesis is the given dice are not unbiased. Since we reject H naught, we conclude that the given dice are not unbiased. So they are biased actually. So similarly, we can able to calculate the uh, fit for normal distribution. So goodness of fit adjusters are generally used to test whether the data agree with the fitted distributions. Oh, okay, thank you.